Welcome back. As promised, we are going to do a drill in this segment. So here it is. Please fit a parabola, and I'm giving you the form here, y, that's the data point of course, is equal to ax squared plus bx plus c, where of course a, b, and c, the quadratic, the linear, and the constant terms are unknown. You're going to fit that parabola to n data points, xi, yi, and I'm going to ask you to formulate this as a least squares estimation in three unknowns, a, b, c, and we're going to write some code that computes and plots the least squares fit. Now I'm going to give you a little bit of code here as scaffolding, and you're going to fit code in right here. I was able to write this in 2 lines. You don't have to write in 2 lines. It can take a little bit more if you want. I will put this code on the course website. This code right here is generating some synthetic data for you that satisfies this but adds a little bit of noise so that the least squares actually has to do some work. This again is going to be the code that you pack in with the solution. Please have your answer be called the variable u, which is a vector with 3 values in it, a, b, and c in that order. And then this code will plot the data for you and plot your fit, and you'll be able to see if you actually got it right or not. Okay? So go ahead and pause the video and try to do this. Now you have to do 2 things, of course. The first thing to do is not Python, is figure out what is the quadratic error function for fitting a parabola, so 3 unknowns instead of 2. Write out the least squares estimation, figure out what that matrix is, what the unknown is, and what that vector is, and then you should be able to implement the least squares solution. So in fact, what you should do is really start with the standard quadratic error function, write it in vector form, differentiate it, set it equal to 0, and solve. That will give you a closed form solution with some matrix algebra for estimating those parameters. Okay? Think about it a little bit. If you're stuck, start the video again. I'm going to show you a little bit of the solution, and then you can pause the video, and we'll keep doing that until we get to the end. All right, so here we go. All right, this is the hard part, by the way. The hard part is always formulating the problem. Once you've formulated it, you just got to sort of turn the crank a little bit. So what's my model? Every y coordinate is equal to ax plus bx plus c. Quadratic term a unknown. Linear term b unknown. Constant term c unknown. I want to solve this using least squares. So what does that mean? Well, I want to figure out what is the distance between every point x, y, and the parabola parameterized by a, b, c. So what is that? It's the same thing. Nothing's different. I take the current y coordinate, I evaluate what the y coordinate would be if I shoved it through the parabola. Here it is right here. And I just subtract the 2, and then I square it. So what did we do with the line? We just didn't have that term right there. I just had bx plus c minus y. Notice, by the way, don't get confused by the squared there. That is nonlinear, but it's nonlinear in the thing you know. This is still a linear equation because a is multiplying something you know, b is multiplying something you know, and c is multiplying a constant, and all those are being added up. Perfectly linear, despite the fact that you have a quadratic term, but it's a quadratic term in the data. Yeah? So there is my delta. So if you got a little stymied by this, okay, no problem. Stop the video now, and now ask yourself, what does the quadratic error function that looks like that sums up all of those? Get it into matrix and vector form, differentiate it, solve, and then write the code. Okay, let's keep going. All right, so here is our classic error function written out algebraically. E of a, b, c, so those are the 3 unknowns, is equal to the sum from I equals 1 to n, those are all the data points, of, well, just delta sub I squared. So there is ax squared plus bx plus c minus y, that whole thing is squared. Notice again that the y's and the x's, of course, are indexed on the i's, but the a's, b's, and c's are not. Now, look, you could slog it out. You could expand this out the way we did with the line. Isolate C, isolate B, isolate A. You don't want to do this. This is a nightmare. This is really where, once you get past 2 parameters, you got to do this linear algebraically. So let's write this now linear algebraically. Well, what are my unknowns? They're A, B, C. That stays unchanged. So we're going to have a vector now just not of slope and intercept, but the quadratic, the linear, and the constant term of the parabola. What is A, B, C going to multiply? Well, the A multiplies the quadratic term, x squared. The b multiplies the linear term, x, and the c multiplies 1. And that, of course, minus y1 is delta 1. So again, row times column minus scalar is the first term in that sum. Next row times column minus this is the second term in that summation. So here now I have an n by 3 unknowns, 3 by 1, n by 1. Now, when I evaluate this, what do I get here? Well, I just get a vector of a bunch of deltas. What are those deltas? They're the vertical distance between the model and the data point. So now it's sounding very familiar. All I had to do was add another column here, another row here, but everything sort of looks the same at this point. Okay, so let's see what we have. Let me call this vector U, A, B, C, and a column vector U. Let me call that matrix X, and let me call that vector Y. And now my quadratic error function looks like this, where again I'm using the vector norm notation in the square. Now, if I just showed you this equation, is this any different than the equation of a line? Well, no. I mean, the only difference is that matrix is a little bit bigger and that vector is a little bit bigger, but from the point of view of having to differentiate this, set equal to 0 and solve, it's exactly the same problem, and there's the beauty of it. Once I've written this in matrix form, I don't care about the dimension of that and the dimension of that. It's all the same to me. Let's see why. All right, differentiate this. What is the derivative with respect to U? It's now a derivative of a vector of 3 partial derivatives with respect to A, B, and C. But in some ways, I don't really care about that because I know that the derivative of this with respect to U is 2 comes down, X transpose comes out, and then it's that term to the power 1, decremented by 1. That looks pretty familiar to me. I can drop the 2 all over again. So now I've got X transpose X U minus X transpose Y. Use the unknown. This is known. Bring the known over to the right-hand side of the equation. And what's left is this little 3 by 3 matrix, still invertible because it's square. Invert it, and I've got U is equal to X transpose X inverse X transpose Y. That is exactly the same formula that we use for solving for a line and intercept. It's just that this matrix is now 3 by 3, and this is going to be 3 by 1, but the solution exactly the same. So once you've formulated this in terms of the matrix times a vector, you turn the crank, and the solution is always the same. In fact, you don't even have to turn the crank anymore. You know what the answer is. It's just a different X, a different U, and a different Y. All right, so let's now do the code. All right. In my version, by the way, there's not a lot of slop in the data, and you can change that by playing with that parameter right there. So as you start to increase the noise in the system, the data will deviate from the parabola, and you can see how your least squares estimation works. So here it is. I'm going to build my 2 lines of code as promised. If you took 3 or 4 lines, it's fine. I just did this particularly compactly using NumPy. So the matrix X has what? A bunch of X squareds in the first column, a bunch of X's in the second column, and a bunch of 1's in the first column. And that's what I'm doing right here. So I'm stacking together the square of the vector X. Those are all the X terms in a vector there, all the X's, and a bunch of 1's. And that axis equals 1 says to just do it in the vertical direction. So now I've got X. I've already got Y because that's this thing right here. Well, right here after I've added noise. And now I've just got to do the least square solution. So I'm going to invert X transpose times X and multiply it by X transpose and Y. U now has 3 values in it, the quadratic term, the linear term, and the constant term, which is what I'm plotting down there, and that's what you're seeing in red. And again, I encourage you to play with that little parameter there and watch what happens as that data starts to have a lot of noise. You'll see that that line cuts through the data very nicely, minimizing, again, the square of the vertical distances. Okay, good. I hope you got that drill. If not, I encourage you to go back and do it all over for you again, because we're going to see that pattern over and over again of setting up these linear systems and then solving the linear systems. All right, we'll pick it up in a few minutes.